Welcome back, everyone, to our lecture series based upon the book Linear Algebra Done Openly. As usual, I'll be your professor today, Dr. Andrew Misseldine. It's good to have you. My hellos come from Cedar City, Utah. And we're starting a new chapter today. We're going to be in chapter 5, which is all about a magical topic known as the determinant of a matrix. The determinant is a multilinear function used to describe some aspects of matrices, and it turns out it's used a lot. I've kind of deliberately postponed its discussion of determinants until near the end of the book, chapter 5, to kind of emphasize that although the determinant is important, sometimes there's an overemphasis on how necessary it is for a lot of linear algebra problems, and so we actually postponed until chapter 5 since we haven't needed it for really anything so far. On the other hand, I do want to mention that we have used the determinant in some places throughout this course here. So if you have the matrix, a 2 by 2 matrix A, whose coordinates, whose numbers are A, B, C, D, right? We had a formula for the inverse of the matrix. The inverse of A was equal to 1 over this number AD minus BC, and then you swap the location of the diagonal entries A and D. You negated the off diagonal coordinates B and C there. And so this right here, this matrix, is an example of something we'll talk about a little more in this chapter, commonly referred to as the adjoint or adjacent of the matrix A. But our topic at hand right now is the following: this number AD minus BC. This number, as we mentioned before, is the determinant of this matrix A. And so it turned out that the formula for the inverse of a matrix, 2 by 2 matrix, depends on this number, which we call the determinant. And the matrix was invertible if and only if the determinant was non-zero. So it was non-singular if and only if this determinant was not equal to 0. And in this case, the determinant was equal to this linear combination of the coefficients AD minus BC. And so what we want to see in this semester is, or in this chapter, I meant to say, is a generalization of this formula among some other applications of the determinant. And so what I want to do in today's lecture is introduce the notion of the determinant and start doing some basic calculations of determinants. All right. And so before we can define the determinant, because the determinant itself is going to be defined recursively based upon what we call minor matrices, it begs that we define what a minor matrix is in the first place. Now, determinants are only going to be defined for n by n matrices, that is, only for square matrices. And so given a square matrix A, we're going to define the ij minor matrix Aij, which is itself is a n minus 1 by n minus 1 matrix. So it has one less row and one less column compared to the original matrix. And that's because the minor is formed by removing the ith row and the jth column of A. Now remember, when it comes to matrices, we always reference the row first. So we have this ij position. We get the ith row first, and then we talk about the jth column. And so when we talk about the ij minor, we're talking about the ith row is going to be removed and the jth column. Let's see an example of this. So take a 3 by 3 matrix. A, you see in front of you 5, 7, 0, 0, 3, 0, and 9, negative 1, negative 6. And let's calculate a couple of minors. Let's first look at the 1, 1 minor. So what the 1, 1 minor would mean is that we're going to remove the first row and the first column. And so we just look at this matrix right here, the positive 3, 0, negative 1, negative 6. And so we record that 2 by 2 matrix right here, 3, 0, negative 1, negative 6. And that's then the associated minor. All right. Next, if we want to do the 1, 2 minor, 1, 2 minor says we take away the first row and the second column. Always do rows and then columns. And so the 1, 2 minor would look like 0, 0. Let me fix that. 0, 9, and -6. All right. The next one is the 2, 2 minor. The 2, 2 minor is formed by removing the second row, second column. And so if we see what we have there, we have the 5, 0, 9, and -6. 5, 0. My zeros sometimes look like sixes. 9 and -6. If we did the 2, 3 minor, we end up with, well, we first take away the second row, third column, like so. That gives us 5, 7, 9, and -1. And then finally, let's do the 3, 3 minor. This is achieved by taking away the third row, third column, which then leaves us with the matrix 5, 7, and 0, 3. Pretty easy stuff right here. These minors, we just take away a row and a column and take away all the entries in those locations. Now, given a 3 by 3 matrix, you're going to have 9 minors, which really every row and column combination you take away is in direct correspondence with every position in the matrix. So 3 by 3 matrices have 9 entries, 3 times 3, so there's going to be 9 minors. If we did a 5 by 5 matrix, there would be 25 different minors we could talk about, 5 times 5 there. So I'm not going to list all of them. I think this example is probably sufficient. So with this definition of minors out of the way, let's talk about what we mean by the determinant. So given a matrix A, and let's say the entries of A are going to be the numbers Aij, and again, this is an n by n matrix, it's important there. The determinant of the matrix, which we'll often denote this as det of A, sometimes it's just called, you'll just write the matrix A with like absolute values around it. That would give us the determinant. Sometimes that might mean something else, so the det notation is a little bit more preferable, but you do see people denote the determinant that way. Also, you'll see people denote the determinant by, you draw the matrix the way you did before, but instead of these like these square brackets we had on the matrix, you'll put these vertical lines with no curling or bending to them whatsoever. So an example of this, we might take the determinant of the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8, 9. And so you'll see that with the straight lines, this means we calculate the determinant of the matrix. It's not the matrix itself. Now, when we compute a determinant, we're going to compute it recursively. That is, we use subcases in order to define the determinant of any given matrix. So as a base case, we're going to use 1 by 1 matrices. Now, if you have a 1 by 1 matrix, it's really just a number. That's all there is. There's just one number right there. And so we're going to define the determinant just to be that number itself. And so for 1 by 1 matrices, there's nothing to it. So if you take a determinant of R, you just get R. And this is, again, this is one of the reasons why this notation can be a little bit confusing at times, because we're not taking the absolute value of the number, we're taking the determinant of the number. Now, the good news is we rarely, if ever, are going to take the determinant of a 1 by 1 matrix, so it's not usually too much of a concern for us. 2 by 2 is often going to be the base case we work with. But in terms of completeness of definitions, a 1 by 1 matrix is a matrix, and its determinant is just considered just to be the single number. Now, for larger matrices, so if you have more than 1 by 1, we define the determinant of the matrix as this linear combinations of the determinants of the minor, of each minors here. So this A11, A12, A1n, these were minors that we have defined previously. So you're going to compute the determinant of the minor, all the minors along the first row. So this would be the 1, 1 minor. You take away the first row, first column. Then you have the 1, 2 minor. You'll take away the first row, second column. Then you would have the 1, 3 minor, the 1, 4 minor, all the way down to the 1, n minor. That is, you remove the first row, nth column. So going along the first row, you then take away always the first row, and then you're going to take away the corresponding columns as you move down. And as you move down this sum, there's going to be these coefficients. There's A11, A12, then the next will be A13, A14, all the way down to A1n. And so these coefficients are the numbers in that first row. The first row, first column, first row, second column, first row, third column, first row, fourth column, all the way down to the first row, nth column. So the coefficient that sits in front of the determinant of the minor will be the entry that's in the row column combination that you're removing. Then also it's important to emphasize that this is an alternating sum. It goes plus minus, plus minus, plus minus, all the way down. And so this last number is a power of -1, because it's plus or minus depending on how you go, but there's always this alternating sum, plus minus, plus minus, plus minus. And so this right here, this sigma notation, is just a closed form of this expansion right here. So it's a combination, it's an alternating sum of entries in the first row times the determinant of the corresponding minors. Let's see an example of that. Actually, before we do that, I want to actually convince you that this definition agrees with the 2x2 determinants we've done before. So if you have a 2x2 matrix whose entries are A, B, C, D, the determinant by the formula we did before, so we're going to have the first row, first column. So this will give you the number A. That's the number in the 1, 1 position. Then we're going to take the determinant of the minor of the 1, 1 minor, which the 1, 1 minor, as you can see, would just be the 1 by 1 matrix D. Then we're going to subtract from that the 1, 2 position, which the 1, 2 position is B. We remove the first row, second column. That'll then give you the minor of the minor will be just the 1 by 1 matrix C. And these are determinants, right? We're not taking absolute values. So this will then give us, well, since the determinant of a 1 by 1 matrix is just the number itself, you'll get AD minus BC, which is what I claimed was the 2x2 determinants before. And so actually, most people can remember this 2x2 formula right here. And so it's because of this that we'll rarely ever use a 1 by 1 case whatsoever. And when it comes to 1 by 1 or 2x2 determinants, you have to remember the rule that you're going to take the product of this diagonal, A times D, and then you're going to subtract from that the product of this diagonal, C times B. And so this AD minus BC formula we use for 2x2 determinants. And so I'm going to use this in the future as we compute 2x2 determinants. So all right, here's the example I was actually expecting here. Let's do a 3x3 determinant. Take this matrix 5, 7, 0, 0, 3, 0, 9, 1, negative 6. If we expand this along the first row, so expand along the first row. So we're going to do the 1, 1 position. So we get the number 5 because it's in the 1, 1 position. Then we calculate the determinant of the 1, 1 minor. So we take away the first row and first column. That leaves behind 3, 0, negative 1, negative 6. We'll come back to that one in a second. We then subtract from that. We're going to do now the 1, 2 position, which is 7. Then we times it by the determinant of the associated minor. We take away the first row, second column. That leaves behind 0, 0, 9, and negative 6. And then finally, we're going to add together the entry that comes from the third position, that is the 1, 3 position. We get a 0 right there. And then we times that by the associated 1, 3 minor, which will give us 0, 3, 9, and negative 1. And so that formula we had seen previously, that's a recursive formula, would expand for a 3x3 matrix in the following manner. So for each of these 2x2 determinants, we would calculate it, and we're going to use that formula from the previous slide. So we get 5 times, we're going to get 3 times negative 6 minus 0 times negative 1. So that's the first 2x2 minor determinant. Then we get negative 7 times, we're going to get 0 times negative 6 minus 0 times 9. And then the last one, we're going to get 0 times, well, who cares, honestly, because whenever you multiply something by 0, the product's going to be 0. So it actually doesn't matter what this minor determinant turns out to be. The product's going to be 0. So I'm going to save us some computational effort and just keep the 0 there at the end. All right. If we continue with this calculation, we get 3 times negative 6, which is negative 18. Then you get minus 0 times negative 1. That's just 0. And so we can subtract 0 if we want to, but really, I'm just going to just leave it as negative 18 right there. Then we get negative 7 times, well, 0 times negative 6 is 0. So we get a 0 there. And 0 times 9 is also 0. So if you subtract that, you still get 0. And then we had a plus 0 from before. And notice because of the zeros, you get another product of zeros, and then that 0 just goes away right there. We just have to do 5 times negative 18, which gives us negative 90, which is the determinant of this matrix. In a little bit, we'll try to give some significance of what this number is measuring. But for now, I just wanted to give us the calculation in mind here. I did want to point out to you that this calculation actually worked out really nicely because of all the zeros we saw. Because we had a entry in the first row that was 0, I didn't even have to bother computing one of the minor determinants because of the factor of 0. And also because this second minor right here had a row of zeros, that led to the minor determinant being 0 as well, so it kind of canceled out. And then even over on the first one, there wasn't any cancellation of everything, but zeros in the presence of a matrix make for much simpler determinant calculations. So we really like zeros, and we're going to kind of see in a little bit how we can benefit from zeros inside of a matrix.